Hi, I'm Andrew Wilson at New York University, and welcome to the ICML 2020 tutorial on Bayesian deep learning. I'm very excited to be presenting this tutorial, and I'd like to especially thank Johan Bremer, Pavel Ismailov, Rajesh Ranganath, Christina Savin, and Hehe for helpful feedback in preparing the tutorial, as well as my students, collaborators, and colleagues, and the ICML program chairs and tutorial chairs for the opportunity. We'll start with a pattern recognition problem where we have airline passenger numbers indexed by time. We'll consider three different modeling choices. Choice 1, a linear function. Choice 2, a cubic polynomial. And choice 3, a 10,000th order polynomial. Pause the video for a moment and consider which choice you would make in order to provide a good description of the data. Most people go with choices 1 or 2. In this tutorial, we'll argue for choice 3, because the real world is a complicated place, and there'll be some setting of the coefficients in choice 3, the WJs, which provide a better description of reality than could be possibly managed by choices 1 or 2, which are just special cases of choice 3. In practice, we're often making something like choice 3 and using neural nets that have tens of millions of parameters to model problems with just tens of thousands of data points, and finding we often get very good generalization. In part 2 of this talk, we'll actually consider models with an infinite number of parameters that at the same time have very simple inductive biases and provide great generalization even on problems with a small number of data points. To begin understanding the motivation for choice 3, it's helpful to think about modeling from a function space perspective. Let's consider choice 1, the linear function, f of x equals w0 plus w1x, and we'll just put a standard normal distribution over w0 and w1. And this will induce a distribution over functions, which we can visualize by sampling from this distribution over the parameters and looking at the different straight lines with different slopes and intercepts that we get. We'll get different w0s and w1s, different straight lines. The gray shade here shows a 95% credible set containing 95% of these functions, and the solid blue curve here shows the expectation of this distribution over functions. In this diagram, we have a conceptualization of all possible data sets on the horizontal axis and the marginal likelihood or evidence on the vertical axis, which is the probability that we would generate a data set if we were to randomly sample from the parameters of our model. The model which we were considering on the last slide can just generate straight lines with different slopes and intercepts, not very many data sets. But because the marginal likelihood is a proper normalizable probability density, it's going to give a lot of mass to those data sets. We could alternatively consider a model like a multi-layer perceptron, which might have a lot of hidden units and layers, and we have a broad distribution over the parameters, and it can generate a wide range of different data sets, but it won't give any one of those data sets very much probability. We could alternatively consider a third type of model, like a convolutional neural net, which is very flexible. It can describe a wide array of different data sets, but at the same time, it has very particular inductive biases, like translation equivariance, which says that if we translate an image, we don't want to change the class label. And this means that these types of models are going to give a reasonable amount of mass also to structured image data sets and provide good generalization on those problems. In order to construct models with good generalization, we'll argue that we want large support, the support being which solutions are a priori possible, and reasonably calibrated inductive biases, the inductive biases being the distribution of support, which solutions are a priori likely. So we can consider the support to be the flexibility, and we want a lot of flexibility. At the same time, we should be careful not to conflate flexibility and complexity. In fact, in part 2, as we've mentioned, we'll be considering models with infinitely many parameters that are extraordinarily flexible and at the same time provide very good generalization, even given very small data sets. By the same token, we should not treat parameter counting as a proxy for complexity. In this figure, on the left panel, we have the same diagram we had on the previous slide. In the other panels, we see what happens as these different models are exposed to a given data set. In green here, we see in the second panel, the model with large support is able to contain a good ground truth description of reality, but it has well-calibrated inductive biases, so it efficiently collapses down onto that good description of reality. In the next panel in blue, we can hardly describe many data sets at all, just straight lines with different slopes and intercepts, and so while the model becomes quickly constrained by the available data, it becomes erroneously constrained and it starts to collapse down onto a bad solution. And in the last panel, we have a flexible model which casts wide enough a net to provide a good description of reality, but it spreads its support too thinly to have good inductive biases and reasonable contraction around that good description of reality. In this tutorial, we'll argue that the key distinguishing property of a Bayesian approach is marginalization rather than optimization. That is, instead of use a single setting of parameters W, we want to use all possible settings of parameters and weight them by their posterior probabilities in what's called a Bayesian model average. And we'll argue that this Bayesian model average will be especially relevant in deep learning. I first became interested in Bayesian deep learning after listening to a talk about optimization, which is perhaps a bit ironic given what I said on the previous slide. We might characterize Bayesian methods as trying to avoid optimization at all costs. Don't just bet everything on a single setting of parameters, use all possible settings of parameters. The argument was being made that mini-batch SGD would converge to flat regions of the loss, which would provide better generalization in deep learning than full batch gradient methods. In this diagram, we have a conceptualization of parameters on the horizontal axis and the value of the loss on the vertical axis, training loss in black, testing loss in red. We can see that a flat solution in train has reasonably low loss in test, whereas a sharp solution has pretty high loss after there's this horizontal shift between the training and the test loss, which will typically happen because our model won't be completely determined by a finite sample. When we evaluate the loss on different sets of points, even if they're drawn from the same distribution, we should get a different optimal setting of parameters. And the shape of the losses should be relatively similar because the training loss is still not a horrible proxy for generalization. Now, if this argument were true and it meant something, then to mean something, the different parameters in the flat region would have to correspond to different functions which provide compelling and complementary explanations for the data. Otherwise, we could just contrive flatness through reparametrization and it wouldn't really mean anything. Then this was an extraordinary argument for following a Bayesian approach and doing marginalization or integration, basically integrating a flipped version of this curve where we want to consider all of those good solutions and weight them by their posterior probabilities. In this sense, it might just be a bit arbitrary to bet everything on just one good solution when we know that there are many. And so there are many reasons to be excited about Bayesian deep learning. Neural nets can represent a variety of complementary explanations for the data, and we'll be seeing this particularly in part 3. And this will lead to better uncertainty representation, which is crucial for decision making. We could think from a practical perspective, if our model could never influence a decision conceivably, then it might not have much of a practical impact. But it will also have a big effect on the accuracy of our point predictions, which is perhaps an underappreciated aspect of the benefits of Bayesian marginalization in deep learning in particular. Because there are all these different complementary solutions, we can form a rich ensemble of high-performing and diverse solutions, and by doing that, we'll often get much better accuracy if we can do this marginalization effectively. Bayesian neural nets were also a gold standard for a wide variety of problems in the second wave of neural nets, led in many ways by Radford-Neal's Hamiltonian Monte Carlo approaches, which don't scale to modern architectures, but we know that, in a sense, there's treasure buried in some direction, and we just need to build the right tools as a community to extract that treasure. And as we started to see, neural nets are also much less mysterious when viewed through the lens of probability theory. Overparametrization, double descent, model construction, and many other properties like being able to fit random labels become very understandable when we think about things from a probabilistic perspective. Why not? These models can be computationally intractable and can involve a lot of moving parts, design decisions, approximate inference procedures, and so on, but they don't have to. And in the last year, there's been really extraordinary empirical progress for Bayesian deep learning, where we now have several methods often providing better practical results than classical training without significant overhead on quite a wide variety of problems. This tutorial will have 4 parts. This first part is about foundations of Bayesian machine learning, particularly with respect to how Bayesian methods could impact deep learning in particular. In part 2, we'll be considering a function space perspective of machine learning. In part 3, we'll consider several practical methods for modern Bayesian deep learning. The goal of this part isn't just to enumerate all of the state-of-the-art methods, but rather to exemplify many of the foundational concepts that we introduce in other parts of the tutorial with several modern approaches. And in part 4, we'll be considering Bayesian model construction and generalization, including deep ensembles and their connection with Bayesian marginalization and how we can build on those connections for the multi-swag approach, which marginalizes within multiple basins of attraction, tempering, prior specification, rethinking generalization, double descent, width depth trade-offs, and a variety of other topics. Now, I'll add a brief disclaimer, which is similar to a nice disclaimer I saw in the NeurIPS tutorial on deep learning with Bayesian principles. This tutorial is not meant to be a review of all things Bayesian deep learning. That may have actually been possible 3 years ago, but I'm excited to say it's not anymore. We're having workshops now on Bayesian deep learning with hundreds of paper submissions. Rather, this tutorial is meant to provide a complementary perspective, which is largely based in my own experiences and expertise. A decent portion will be based on my own work. In a sense, it's what I would tell myself if I could build a time machine and go back in time. That said, if you feel I should have included something, please send me an email and I'll try to include it next time. So let's go back to this airline passenger number example and really forget everything that we know about statistics and machine learning and think about the foundations and use this example also to set up a lot of notation that we'll use throughout the tutorial. So we have these n training points or targets, observations, y, and they're indexed by x's, x1 up to xn. Generally, the x's could be like time, spatial locations, images. And we want to make a prediction at some arbitrary test input, x star. In this case, could be like airline passenger numbers in 1961. Now, just pause the video for a moment and think about a step-by-step procedure that you might have followed just knowing what you knew in high school in order to solve this problem. If it were me in high school, I would start by thinking about the functional forms that I'm familiar with, like sines, cosines, exponentials, polynomials, and then I would create a functional form that I thought would be a reasonable description of what I'm seeing, and it might have some free parameters, and I would specify an error function, which could be like the squared distance between the outputs of my function and the training observations, and I would minimize that error function with respect to my parameters to learn those parameters. But this approach would involve a lot of ad hoc design decisions, like why squared error and not absolute error, for instance. We can instead follow a probabilistic approach where we suppose that our observations are drawn from a noise-free function, f of xw, plus, for example, additive Gaussian noise with noise variance sigma squared. And we can then use this observation model to form a likelihood, and then we can maximize that likelihood with respect to our parameters and learn those parameters, and then use our conditional predictive distribution given those parameters to make our predictions. We can see by taking logs of the likelihood that if we follow this approach, we'll get exactly the same point predictions as we had using the approach on the previous slide where we just specified the squared error function. However, in this approach, the design decisions are a bit more interpretable. We probably have some intuitions, for example, about whether we want to use Gaussian noise. Perhaps if we thought there were outliers in our problem, we might use a heavy-tailed noise model like a Laplace distribution, and that would lead to an absolute value error function. So we can make different design decisions here and derive different loss functions. If we believe our model, f of xw, to some extent, we can also get an estimate of the noise variance in the data. Now, remembering what we know about statistics, you may be familiar with the idea that either of those approaches could lead to what's called overfitting, where we get very low training loss, but we get very bad testing error. In order to combat overfitting, it's quite popular to introduce what's called a regularizer, where we add some kind of complexity penalty, like we want to penalize the magnitude of the weights in our model. But this also involves all sorts of heuristic design decisions, like how do we know whether we want large weights or small weights? It would totally depend on the parameterization of our model. What is complexity? How much should we penalize it? We could use some kind of lambda parameter, maybe determined through cross-validation, but what would be our validation sets? And if we had several lambda parameters, then we'd have a curse of dimensionality in estimating those parameters. We can gain some interpretability by thinking about maximizing a log posterior, which would equal a log likelihood plus a log prior, and the log prior could be interpreted as a regularizer. But this really isn't a Bayesian approach. There isn't much you need to know in order to use a Bayesian approach for your own research. We have Bayes' rule here, which is often expressed as a posterior being proportional to a likelihood times a prior. The normalization constant is the marginal likelihood, what we were considering on the vertical axis of that plot, where we had all possible data sets on the horizontal axis. The sum rule says the marginal distribution of P of x is equal to the sum over the joint distribution of P of x and y, summing out y. The product rule says that the joint distribution over x and y is equal to the conditional distribution of P of x given y times P of y, or the conditional distribution of y given x times P of x, and we can derive the Bayes rule from the product rule. Now, ultimately, we want to compute the unconditional predictive distribution, P of y, given our data, bold y, but not given parameters. And so the sum and product rules give us this integral in equation 11. The integral of P of y given the parameters times the posterior over those parameters given the data y. And so this is called marginalization because we see w doesn't appear on the left side, it does on the right. In words, this integral is saying, let's not just use one setting of parameters, let's use all possible settings of parameters weighted by their posterior probabilities. And this isn't a controversial expression, it's a direct consequence of the sum and product rules of probability. This model average represents what's called epistemic uncertainty over which function fits the data. There are many different functions corresponding to different settings of the parameters, and we're not sure, given a finite sample, which is the right description of the data. By representing epistemic uncertainty, we can have some robustness against overfitting. We can also view classical training as a special case of this approach, where we have an approximate posterior Q of W given our data Y equal to just a point mass, a delta function centered on the map, the regularized maximum likelihood solution of parameters. We can see that if we substitute this in, we're just going to get our conditional predictive distribution given those maximum likelihood or map parameters. We can also see then that Bayesian and classical approaches will be similar when the posterior is highly concentrated around a setting of parameters, which of course is exactly not the case in deep learning, where we have neural nets that are very diffuse in their posteriors, and also the posteriors capture a variety of different models corresponding to complementary explanations of the data. So we're going to especially want to do this integral in deep learning. We can also see that we can probably do a lot better than classical training in terms of estimating this integral by using some fairly simple posteriors, which might not be good descriptions of the exact posterior, but are still a lot better than a point mass. So we can definitely improve our estimates without needing to have, an exact approximation of this integral, or an exact representation of this integral. Now, there are fundamental differences between Bayesian model averaging and some types of model combination. In particular, the Bayesian model average is meant to represent a statistical inability to distinguish between hypotheses given limited information, but the assumption is that one of those hypotheses, one setting of those parameters, is the correct setting of parameters. And as we get more and more data, our posterior over our hypotheses, our parameters, will collapse onto a particular setting and will recover the maximum likelihood solution. So this is different than some approaches to ensembling and model combination, which work by enriching the hypothesis space and assuming, for example, that combination models might be a correct description of reality. Now let's exemplify some of these ideas with a few applications. Suppose we flip a biased coin with a probability lambda of landing tails. I'd like you to pause the video and answer these three questions. 1, what is the likelihood of a set of data y1 up to yn? So we're just doing n flips, maybe we see m tails. 2, What is the maximum likelihood solution for lambda? 3. Suppose the first flip is tails. What is the probability that the next flip will be tails using our maximum likelihood estimate for lambda? You can assume m tails and n flips. So the likelihood of our data is just a product of Bernoulli distributions, two possible outcomes. Here we have y equals 1 if yi is tails, and y equals 0 if yi is heads. If we don't care about ordering and we observe m tails, then our likelihood is a binomial distribution. M tails here. Probability of getting tails is lambda. And we can easily maximize this likelihood. You could try taking logs of this expression, then derivatives with respect to lambda, setting those derivatives to equal to 0, and so on. And we'll get the solution that the maximum likelihood setting of lambda is m over n, where we have m tails and total flips, which in a sense is kind of intuitive, but on the other hand is kind of problematic. Why do you think this estimate might be problematic? And in considering this question, think about the third part of the problem. What's the probability that we would get tails on the next flip, assuming we've done one flip and we've just observed tails using this estimator? Pause the video and think about the problem for a moment. So if we substitute in m equals 1, n equals 1, we're saying there's a 100% chance that the next flip was tails. Do you believe that? Of course not. And when we arrive at a clearly unbelievable prediction, it's usually because some part of our modeling procedure has not honestly represented our beliefs. Let's think about a Bayesian approach to this problem. If we choose a prior, p of lambda, proportional to lambda to the alpha, 1 minus lambda to the beta, then the posterior, after we multiply the likelihood against the prior, will have the same functional form as the priors. This is called a conjugate prior. A beta distribution has this functional form. The gamma functions here are for normalization. We can analytically compute the moments of the beta distribution. Here we have visualizations of the beta distribution corresponding to different settings of its parameters, a and b. We can see in the top right panel, if we want to express the belief that we don't know what the bias is, then we can use a uniform distribution, setting a and b equal to 1. And this means lambda is equally probable for any value between 0 and 1 a priori. And so we can express, even the idea that we really just don't know using a prior distribution. We don't need to have an informative prior. However, we might want to consider a prior that says, well, we think that the bias is probably close to a half, but we're not going to say it's definitely a half. Just choose whichever prior is an honest reflection of your beliefs, even if your belief is, I don't know. So we can multiply our prior with our likelihood to get our unnormalized posterior. This is a beta distribution. We can compute its moments and use the posterior expectation over lambda for our predictions. We can see in equation 27, it's m plus a over n plus a plus b. Now let's consider a few questions. It's good to do some sanity checks here. Well, what's the probability the next flip is tails? Let's suppose that a and b are 1. We can see that it's not going to be 100% if m is 1 and n is 1, so that's good. What happens when we make a and b really large? Well, the prior starts to dominate, so that gives us a strong prior. If we make the data really large, then both n and m will be large, and m over n will dominate in this estimate, and we'll recover the maximum likelihood solution, which is what we want. That's a good sanity check. And now I'd like you to consider this fourth question, which is conceptually very important. Does the map estimate what we get when we take the argmax of the log posterior over lambda, which is equal to the argmax of the log likelihood plus the log prior, with a uniform prior over lambda, give the same answer as Bayesian marginalization to find the probability that the next flip is tails? Pause the video and think about this question for a minute. So if we have a uniform prior over lambda, then log p of lambda won't affect our optimization in equation 31, and we'll just get the maximum likelihood solution. And we just saw that when we do marginalization, we get a different answer than the maximum likelihood solution, even with a uniform prior. So I can't emphasize enough that we should not interpret Bayesian methods as regularizers in optimization. There is a conceptually very important difference between marginalization and regularized maximum likelihood optimization. And that difference will be practically crucial when we're thinking about Bayesian methods in deep learning. Let's consider one more example. Suppose we have observations y1 up to yn drawn from an unknown density p of y. We'll start by specifying an observation model. We'll suppose that the points are drawn from a mixture of Gaussians, and in order to estimate this unknown density, we'll learn the parameters of this mixture of two Gaussians. Parameters here are the weights, the means, and the variances. So we can use the observation model to form a likelihood, and I've just written it down here. And I'd like you to pause again and think about choosing a setting of parameters which will provide a lot of likelihood without having to take derivatives and stuff like that. You can just kind of look at this expression and play with a few settings and find something, and just think about the means and the variances. Don't worry about the weights. So if we make, for example, the mean of the first component equal to one of the data points, then this x will disappear. It'll just be 1, and we get this normalization constant, w1 over square root 2 pi sigma 1 squared. And then we can make sigma 1, the variance or the standard deviation, very small for the first component. And then this term will blow up. And the other term we can use to assign density to all the points. So we're not multiplying against zeros, and the likelihood goes to infinity. Now, do we believe this solution? Of course not. We typically wouldn't believe our data are comprised of point masses. And when we reach an unbelievable solution, it's typically because we haven't fully represented our beliefs in our modeling procedure. We could introduce a regularizer, or a prior, which would go to 0 faster than the likelihood goes to infinity as the variance parameters go to 0. But we might want to include the point mass solution as long as it's one of an uncountably infinite number of solutions, which we can do through full Bayesian marginalization, in which case we can use extremely flexible models, even infinite mixtures of Gaussians, corresponding to Dirichlet process mixture models, and achieve good generalization even with a small number of points. Now, ultimately, as we've been saying, we wish to compute a Bayesian model average corresponding to our unconditional predictive distribution, P of y given data, rather than our conditional predictive distribution, P of y given parameters W. This unconditional predictive distribution is equal to the integral of our conditional predictive distribution times our posterior P of W given data. This is just an expression of the sum and product rules of probability. Rather than use a single setting of parameters, we want to use all possible settings of parameters weighted by their posterior probabilities, which is going to be especially impactful in deep learning, where we have highly diffuse posteriors containing different settings of parameters that correspond to a variety of compelling and different solutions to a given problem. For most models, including Bayesian neural nets, this integral is not analytic. It's common to use what's called a simple Monte Carlo approximation, where we take an average of the conditional predictive distributions for different settings of parameters sampled from an approximate posterior Q of W given data. We find these samples typically through one of two approaches. Deterministic methods approximate the posterior distribution with some convenient distribution Q. Although the integral can't be computed in closed form, typically we can represent the unnormalized posterior analytically. It's just the likelihood times the prior. Q, our approximate posterior, is chosen for convenience, often so that it's easy to sample from, like a Gaussian distribution, in which case its parameters would be its mean vector and its covariance matrix, which we choose typically to make Q close to P in some sense. For example, variational methods find these parameters by minimizing the KL divergence between Q and P. As we mentioned earlier, classical training is a special case of approximate inference, where our approximate posterior is just a point mass centered at the maximum likelihood or regularized maximum likelihood map setting of parameters. The Laplace approximation is another popular deterministic method, which we'll discuss further in part 3. Expectation propagation is another popular approach, and there are several others. We could alternatively consider Markov chain Monte Carlo, which forms a Markov chain of approximate but asymptotically exact samples from our posterior. Metropolis Hastings is a popular MCMC approach. Hamiltonian Monte Carlo uses gradient information and was very successfully developed by Radford Neal in the mid-90s for Bayesian neural nets. Recently, stochastic gradient MCMC methods have been very up and coming and exciting approaches in Bayesian deep learning because they algorithmically resemble SGD, which means they can be applied in a wide variety of applications where you might otherwise use classical training, but often with better results. Stochastic gradient Langevin dynamics and stochastic gradient Hamiltonian Monte Carlo are stochastic gradient MCMC approaches we'll discuss in part 3. Later, in part 4, we'll also argue that we may sometimes want to avoid the simple Monte Carlo perspective in equation 33. Really, what we're most interested in, ultimately, is estimating this unconditional predictive distribution in equation 32 under computational constraints. And from this perspective, it's helpful to think of estimating that integral as an active learning problem under constraints, in which case the deep ensembles method can be very compelling as an approximate Bayesian method, which we'll discuss in part 4. That's the end of part 1. In part 2, we'll be considering a function space perspective. Hi, I'm Andrew Wilson, and welcome back to part 2 of the ICML 2020 tutorial on Bayesian deep learning. In this part, we'll be considering a function space perspective of machine learning. We'll cover Gaussian processes, infinite neural nets, how training a neural net is like learning a kernel, Bayesian non-parametric deep learning, and several other topics. From the function space perspective, the parameters in isolation are entirely divorced from the statistical properties of a model. In part 1, we considered how in regularization, whether or not we want large weights or small weights entirely depends on the parameterization of the function that we're using. Yet we focus most of our modeling efforts on learning parameters W. What we really care about are how those parameters W combine with the functional form f of xw. Ideally, we want to perform inference directly in function space. Let's return to the example that we considered in part 1, where we had a distribution over functions induced by a distribution over parameters in a linear model. We'll consider f of xw equals w0 plus w1x, and we'll place a standard normal distribution over w0 and w1. We can sample from that distribution to get different values of w0 and w1, corresponding to different straight lines with different slopes and intercepts. The gray shade here corresponds to a 95% credible set. 95% of these functions are in that shade. And the solid blue line corresponds to our expectation of this induced distribution over functions. We'll now consider the more general model class, where we have an inner product of a vector of weights w with a vector of basis functions phi. The entries of phi, for example, could be 1, x squared, x cubed, if we're considering a polynomial basis. We could alternatively consider a Fourier basis. This model class is quite general. And we'll place a Gaussian distribution over W with mean 0 for convenience and covariance matrix sigma W. Now I'd like you to pause the video for a second and see if you can derive the moments of the induced distribution over functions given by equations 38 and 39. Now, all of the randomness in this model is coming from the distribution over parameters W. So we can pull phi out of the expectation, it's just deterministic, and we can evaluate the expectation over W, and by definition, in this case, it's just 0. So the mean of this induced distribution over functions is 0. Now, f of xi and f of xj are two different random variables corresponding to querying our random function at two different input points, xi and xj. So the inputs could be time, spatial locations, whatever is indexing our random function. We can use the definition of covariance and derive the covariance function, also known as the kernel function in this case, as the inner product of phi of xi with phi of xj under sigma w. Now I'd like you to consider whether there are any higher moments in this induced distribution over functions. In this case, there are no higher moments because we just have a sum of Gaussian random variables in equation 40, and Gaussians are closed under addition. In fact, f of x is a Gaussian process with a mean function m of x and a covariance function, or a kernel, kxx prime, for two arbitrary inputs, x and x prime. In this case, we can actually do inference directly over f of x instead of over parameters w. Formally, a Gaussian process is a collection of random variables, any finite number of which have a joint Gaussian distribution. We can use a Gaussian process to define a prior over functions. This notation here, f of x is distributed as a GP, means that any collection of function values queried at any collection of inputs, x1 up to xn, these could be time, spatial locations, images, etc., has a joint multivariate normal distribution with a mean vector mu defined by the mean function of the Gaussian process, and a covariance matrix K defined by the covariance function, or kernel of the Gaussian process, queried at all possible pairs of inputs, x1 up to xn. In the bottom left panel here, we have samples from our induced distribution over functions. To create these samples, I chose a bunch of input points, a bunch of x's, and then I formed my multivariate normal distribution by building up my mean vector mu, evaluating my mean function, in this case 0, at all the input points that I've chosen, and forming my covariance matrix by querying my kernel at all possible pairs of the inputs. I then sampled from that multivariate normal distribution to get the black dots, the random function values. And then I sampled from exactly that same distribution 2 more times to get the purple curve and the green curve. Here I've just joined the dots together. The gray shade again corresponds to our 95% credible set. And the blue curve here corresponds to our prior mean function, in this case 0 for convenience. In the right panel, I've conditioned on some data denoted by crosses, and I've sampled several posterior functions in black, purple, and green. We also have the posterior mean function in solid blue, which we can use to make point predictions, and the 95% credible set in gray shade. Very importantly, all of the statistical properties of these functions are controlled by our kernel. And in this case, we're using what's called an RBF kernel, also known as a squared exponential or a Gaussian kernel. This kernel has the functional form a squared times the exponential of the negative Euclidean distance between our two inputs, x and x prime, over 2L squared, our length scale. It incorporates the very intuitive inductive bias that functions that are close together in the input space should be more correlated than functions that are far away in the input space. For example, airline passenger numbers in 1951 and 1952 should be more similar than airline passenger numbers in 1951 and 1960. So this is a very natural inductive bias. The extent of the correlations is controlled by the length scale hyperparameter L. If L is very small, the function values become uncorrelated. We just have a white noise process. If L is very large, then the function values become all very correlated. A is the amplitude hyperparameter. If A is large, then the amplitude of these functions will be large. In the top panel here, we have visualization of the entries of our covariance matrix when we have 1D ordered inputs. We can see that there's this strong diagonal band where we have highest covariance, and then the covariances decrease away from that band as we increase distance in the input space. So let's consider the distribution over functions that we get when we have particular settings of our length scale and our amplitude parameters, L0 and A0. Here we have our sample prior functions and our sample posterior functions. Pause the video for a moment and think about whether these sample functions look strange to you in some way. And it might be a little bit subtle. To me, these functions look a bit too wiggly. They're varying a little bit too quickly. They're a bit too complex. The mean shoots back down to the prior mean a bit too fast. So to me, that seems like the length scale is too small. Now let's see what happens as we increase the length scale. Perhaps here we've increased the length scale a bit too much. We see now that the functions look too slowly varying, too simple. They're over-smoothing the data. Let's consider again the marginal likelihood that we considered in part 1 of this tutorial. We can form the marginal likelihood in this case by integrating away our Gaussian process, P of f. The marginal likelihood, again, is the probability that we would generate a data set if we were to sample from this distribution over functions. Now, if we have a very small length scale, we just have a white noise process. So we're going to be able to generate all sorts of different data sets, but they're all going to be pretty different from one another. So if we keep sampling from that distribution over functions, well, we won't see the same thing again. If we have a very large length scale, then this induced distribution over functions is pretty simple. As we saw, everything looks sort of like a straight line. Everything is pretty similar. And so we're not really generating that many data sets with very much probability using that large length scale in red. For a given data set, the marginal likelihood will have an Occam's razor property where it will automatically favor a model of appropriate complexity. This is described very eloquently by David Mackay, both in his PhD thesis and in his book on information theory. It's also described in the Gaussian process for machine learning book by Rasmussen and Williams. If we optimize our marginal likelihood with respect to length scale, we get the green fit here, which intuitively has an appropriate level of complexity. If we had to choose between one of these curves, we'd probably choose the green curve. Now, we opened this part of the tutorial by deriving covariance functions from classical weight space models. And then we said, well, let's just use a Gaussian process with an RBF kernel. Now let's derive where that RBF kernel comes from. We'll again consider an inner product of weights and basis functions, in this case, not expressed using vector notation. We'll put a Gaussian distribution over our weights, and we'll use as our basis functions Gaussian bumps centered at points Ci, as drawn in this diagram. We can grind through the algebra, revert to the definition of our covariance function, and get our covariance function in equation 55. Now let's consider what happens as we let the number of basis functions, j, go to infinity. We'll want these basis functions to cover the whole real line, so we'll let Cj, the center of the jth basis function, be log j, and C1, the center of the first basis function, be minus log j. If these basis functions are equally distributed, then the difference between the I plus first basis function and ith basis function will be 2 log j over j. So we see that that goes to 0 as j goes to infinity, which is why I used log j for the endpoints. I could have used root j, for instance, but not j. And the expression for the kernel in equation 57 becomes a Riemann sum, an integral, with limits c0 and c infinity, in this case, minus infinity and infinity. We can substitute in our expression for the basis functions and evaluate this integral in closed form and get something that's proportional to the RBF kernel. Now, this is a very extraordinary result. I'd like you to pause the video and just consider what we've done for a moment. We've actually shown that by thinking from a function space perspective, we can use a model with an infinite number of basis functions using a finite amount of computational resources. So in part 1 of the talk, I opened with this question about how we might model airline passenger numbers. And I said, I'd like to use the 10,000th order polynomial from the 3 choices that we were considering. And you might have wondered, well, carrying this argument to its limit, are we even going to be able to store these models in memory, assuming that we want to use them? And in fact, what we're seeing here is we can use something like an infinite order polynomial. We can use a model that is extraordinarily flexible. In fact, this is a universal approximator, and we can see that by looking at this derivation. If we collapse these basis functions onto point masses, we can have just densely dispersed point masses with different heights. But we've also seen that this model can generalize very well. It has very intuitive inductive biases. So we should be very careful not to conflate flexibility with the complexity of our model class. And we should also be very careful not to do parameter counting as a proxy for complexity. Here we're seeing that we can actually use models with an infinite number of parameters that in some sense have fairly simple inductive biases and provide very good generalization. In this diagram where we have all possible data sets on the horizontal axis, we're saying we want to have heavy tails, we want to support all sorts of different data sets, but we also want to have mass in reasonable places. And we can get that, in this case, through the inductive biases of the kernel function. I'd like to add a brief note about the mean function. In this tutorial so far, and in many texts about Gaussian processes, the mean function m of x is often taken to be 0 for notational convenience. But in fact, we can use any deterministic mean function without fundamentally changing the modeling procedure. And it's usually pretty standard to subtract off the empirical mean and then use the zero mean GP or subtract some kind of deterministic mean function and then add it back later. Also, typically the covariance function of the kernel is really the key object of interest. And there are often degeneracies between specifying the mean and covariance function, in which case often it's typically preferred, therefore, to do the modeling in the covariance function. For example, the kernel function shows up in the Occam factor term we get in the marginal likelihood, a log determinant, but not the mean function. That said, a mean function can be a great way of incorporating scientific inductive biases into a model. There's sometimes a tension between using an interpretable, scientifically motivated model, for example, a model with physically interpretable parameters, and some black box function approximator. In actuality, this is often a false choice. We can often use both in the sense. We can use, as our mean function, that scientifically motivated model, that parametric approach which has interpretable parameters, and then we can, at the same time, use our Gaussian process with an RBF kernel to allow for a non-parametric relaxation around that mean function to account for inevitable model misspecification. So we can really have both. We can use that mean function of whatever other model we would have used to calibrate the inductive biases of our approach, and we can concentrate our distribution of functions as closely or as loosely as we like around that scientific mean function. Interest in Gaussian processes in the machine learning community was triggered by work that Radford Neal was doing on Bayesian neural nets. He really embraces this idea that we should build very flexible models, and accordingly was pursuing the limits of very large Bayesian neural nets. And he showed that as we let the number of hidden units in a Bayesian neural net go to infinity, we get a Gaussian process. Here, let's consider the simple neural net f of x equals a bias plus a sum of a bunch of hidden units with hidden unit weights ui. And with fairly general assumptions, one can show using a central limit theorem argument and not even requiring, for example, that the parameters have Gaussian distributions, that we'll get a Gaussian process in the limit as j goes to infinity. And we can derive the moments of the Gaussian process just as we already have been doing in other examples. We can make particular design choices, like we can let our activation functions be error functions, and we can use a Gaussian prior over our hidden unit weights and derive a neural network kernel in equation 69. Here we have samples from a GP with this neural net kernel. We can see that they're non-stationary, that at a high order, the statistical properties in the center are different than in other regions. Unlike, say, the RBF kernel, which is translation invariance, it's a very flexible model. It could look different in different parts of space, but in a high order, the statistical properties of the functions in those types of kernels will be similar in different regions of space. So this result, that an infinite neural net converged to a Gaussian process, was very exciting in the machine learning community. And in some cases, it drove the idea that we ought to just use Gaussian processes instead of neural nets. At the time, people were becoming very frustrated by all sorts of design decisions associated with working with neural nets, like how many hidden units do we want? How many hidden layers? What are the activation functions? What optimization procedure are we using? What what learning rate schedule are we using with that optimization procedure? And the lack of a principled framework to answer these types of questions. Gaussian processes, by contrast, were very simple and interpretable and flexible, and you could write the same 10 lines of code and get the same answer anywhere in the world. Now, David Mackay was a big supporter of Gaussian process research, but at the same time, he was a bit of a contrarian. He wrote this essay in an edited book on neural nets where he has this quote: "How can Gaussian processes possibly replace neural nets? Have we thrown the baby out with the bathwater?" And what he meant was that when neural nets were being developed, they were envisaged as becoming intelligent agents that could discover interesting hidden representations in data. And while Gaussian processes had all of these nice statistical properties, they were also basically just smoothing devices. In which case, are we throwing the baby out with the bathwater and treating GPs as replacements for neural nets? The answer to this question is to build more expressive kernel functions which can discover interesting hidden representations in data. Although kernel methods and Gaussian processes and neural nets are somehow treated as competing approaches, they're often actually quite complementary. What we get with a neural net is a way to create highly adaptive basis functions which have very good inductive biases for a number of different application domains, such as image recognition. What we get through a kernel method in a Gaussian process is a way to have an infinite number of basis functions using a finite amount of computation. We can combine both of these properties together into approaches like deep kernel learning, where we have a neural net transforming the inputs of a base kernel to create a deep kernel, which is then jointly trained through the marginal likelihood of the Gaussian process as one model. So this gives us an infinite number of highly adaptive basis functions. Importantly, this is quite different than what we would get if we were to just use a neural net as a feature extractor, train the neural net, and then apply a GP to the result. Rather, deep kernel learning here is a one-step end-to-end procedure. It's a single model, and it's trained through the marginal likelihood objective. We can use Gaussian processes with deep kernels to do representation learning. In this example here, we have a Gaussian process with a deep kernel applied to the Olivetti faces problem, where we're considering faces with different orientation angles, and we're trying to predict the orientation angle for new faces. We can see, projecting what the model learns into 2 dimensions, that it discovers that faces with similar orientation angles, here each face is given by a line segment, and the orientation angle is given by the slope of that line segment, are clustered together, are similar in some way. We can also see this by visualizing the learned covariance matrices that we get, ordering the faces by orientation angle. In the left 2 panels, where we're using deep kernels, we see a pronounced diagonal band, which shows that the model learns that faces with similar orientation angles should be more correlated. This is non-Euclidean metric learning. In a sense, we can describe what a neural net is doing as learning a flexible non-Euclidean similarity metric for the data. In this sense, training a neural net is a lot like learning a kernel. In the far right panel, we have the entries of the trained RBF kernel matrix, which we see are quite diffuse. Euclidean distance is just not a good proxy for similarity in this application. Looking at Euclidean distance of vectors of pixel intensities is not going to describe what we need to describe in order to solve this kind of representation learning problem very effectively. In this example, we're considering a discontinuous step function. And we see that a GP with a deep kernel in green here, the green shows the 95% credible set, describes that data very effectively. A GP with a spectral mixture kernel, a different type of kernel, is shown in red. It still fits the data all right, but it sort of over smooths. We see a GP with an RBF kernel fit in blue. From the perspective of a GP with an RBF kernel, even though this is a flexible model, this kind of data is a very unlikely draw from the prior. We would have to sample for a very, very long time to see anything like this step function. And so since we can learn the noise here, the model is just saying, well, it's quite probable, if we believe the GP with the RBF kernel, that this data is basically just noise and will have a very simple fit and a lot of uncertainty. So this example shows that Gaussian processes, for example, don't necessarily oversmooth the data or have trouble fitting discontinuous data. It totally depends on the kernel. And with a deep kernel, we can learn this kind of discontinuous step function data. Here we've applied a deep kernel structured with an LSTM network to an autonomous driving application where decision-making with predictive distributions is very important. We don't want to just know where lane boundaries might be, but we want to know, error bars on where these lane boundaries could be in making decisions. And we can see in the bottom row here that the predictive distributions do a good job of capturing the ground truth, and the point predictions are also better than the point predictions that what we get if we use the classic LSTM neural net. Conventionally, Gaussian processes have suffered from computational constraints. We need to solve a linear system involving our n by n covariance matrix for n training points, and also compute log determinants and derivatives of log determinants, which incurs naively an n-cubed computational cost. And exact Gaussian processes have often been intractable for problems with more than a few thousand points. Recently, by embracing advances in hardware, Krylov's subspace methods have been developed that enable very scalable exact Gaussian processes through GPU acceleration and parallelization. And so in a sense, deep learning has progressed not only through advances in methodological design, but also by building algorithms that can really benefit from hardware acceleration, by thinking about how to benefit from systems. And GPyTorch, this package here, really is inspired by that approach in order to scale Gaussian processes with exact inference to very large problems. And when we do that, we can see that GPs with deep kernels often outperform standalone deep neural nets. Also, we can see that when we scale an exact Gaussian process to large problems, we can really realize the benefit of a non-parametric representation. As we add more and more data points, we can see that the error decreases very substantially. With a non-parametric method that has an infinite number of basis functions, the capacity of the model scales automatically with the amount of available information, unlike a parametric model, which is entirely determined by a finite number of parameters. Many approximate scalable inference techniques for Gaussian processes introduce low-rank kernel matrices. So this would apply to inducing point methods, stochastic variational inducing point methods, as well as random feature expansions, which basically turns the model into a parametric method. And we can see that on really large data sets, the gap between the scalable exact GPs and the approximate GPs is especially large. There are several other popular Gaussian process libraries, such as GPFlow, GPy, BowTorch for Bayesian optimization, that's black box optimization, automatic ML, hyperparameter tuning, A/B testing. And these libraries have different algorithmic foundations and use cases. There's also a lot of additional work on combining Gaussian processes and neural nets in various different ways. For example, Gaussian process regression networks and deep Gaussian processes build hierarchical models, replacing neurons in neural nets with Gaussian processes. Several other recent works have extended Radford-Niel's limits to multi-layer neural nets and other architectures like convolutional neural nets. And those limits are also very related to neural tangent kernels, which have been a very hot topic in deep learning recently, where we take infinite neural net limits and derive kernels, which have recently achieved fairly promising empirical results. Now, most of these kernels from infinite neural net limits have fixed covariance structure. And we described how training a neural net in many ways is like learning a kernel. That's what's doing the representation learning. And so bridging this gap and developing these infinite limits so that we can also do kernel learning, I think is a very exciting direction for future work in this space. Now, there are many ways to realize Bayesian principles in deep learning, in addition to the standard approach of marginalizing distributions over parameters in a neural net. In this part, we've really been considering how we can use neural nets to provide inductive biases for Gaussian processes for a Bayesian non-parametric approach to deep learning. In general, combining principles of Bayesian non-parametrics with deep learning is a very exciting area for future work. That's the end of part 2. In part 3, we'll be considering practical methods for Bayesian deep learning. Hi, I'm Andrew Wilson at New York University, and welcome back to the ICML 2020 tutorial on Bayesian deep learning. This is part 3, methods for practical Bayesian deep learning. In this part, we'll be using several modern approaches for highly practical Bayesian deep learning to exemplify many of the foundational concepts that we've introduced in other parts of the tutorial. While I've long been interested in Bayesian machine learning, I ironically became quite interested in Bayesian deep learning after listening to a talk about optimization. The irony is that I might consider Bayesian approaches as trying to avoid optimization at all costs, rather than use one parameter, use all the parameters and weight them by their posterior probabilities. The argument being made was that mini-batch SGD would converge to flatter regions of the loss than full batch gradient methods, and therefore provide better generalization. In this figure, the loss is on the vertical axis, train in black, chest in red, and there's a conceptualization of parameters on the horizontal axis. We can see that a flat solution has still reasonably good testing loss, but a sharp solution has pretty bad testing loss once there's this horizontal shift between train and test, which happens because our model won't be entirely specified by a finite amount of data. And in fact, we would want the different optimal solutions to change as we query our loss on different sets of data, even if they're from the same distribution. At the same time, the shape of the loss is unchanged because we imagine that the loss is still a reasonable proxy for generalization. In actuality, it will change a bit, but not necessarily that much. Now, this was actually a really great argument for Bayesian integration, because in order for this to be true, the flat regions of the loss would have to have parameters corresponding to very different functions, which would provide complementary explanations of the data. Otherwise, we could just contrive flatness, for example, through reparameterization. It wouldn't really mean that much. And if that's the case, then we have all of these low loss parameter settings that are providing complementary explanations of the data, then we really, really want to do that integral. We want to use all these parameters, and it's kind of arbitrary in a sense to say, well, let's just bet everything on one hypothesis. We want to integrate a flipped version of this curve. And that's going to give a very different answer than just using one solution. In particular, recall that the Bayesian model average here, given by this integral, says that we want to use a conditional predictive distribution given W, weighted by the posterior distribution W given D, and integrating over all possible values of W. That's why it's called marginalization. We're not depending on W anymore. We've marginalized it out when we find this conditional predictive distribution. The posterior, W given D, often the loss is taken as the negative log posterior for neural nets, is extremely complex, containing many complementary solutions, which is why Bayesian model averaging is especially significant in deep learning, more significant for neural nets than for most other model classes. In order to come up with a really good approximation of this integral, however, we're going to really need to carefully understand the structure of the neural net loss landscapes. Towards that end, we show that if you retrained a neural network twice and got different architectures, different solutions, different basins of attraction, you could actually find subspaces along which these different solutions were connected, meaning that you could walk from one point to another along a curve in this subspace, and the training loss wouldn't change very much as we traverse this curve. And so this is a surprising result, because if we take a direct linear path between the different solutions found by training SGD with different initializations, we often occur incredibly high loss, almost 100% training error. And so, in a sense, the intuition is that the points were isolated, but in fact, there are subspaces along which they aren't. And this actually means, in a sense, that we're not even finding local optima when we train SGD for these neural nets. We're just finding these kind of basins of attraction, and there's some directions along which they're extremely flat, and we can walk from one solution to another. And we can find these paths by minimizing the loss that we found used to sort of for SGD training, like cross entropy, uniformly in expectation over the curve. So this corresponds to something like a line integral of cross entropy normalized by arc length. So in this visualization, we have a two-dimensional slice through a very high-dimensional loss surface. And each point in this plane here corresponds to an affine composition of three high-dimensional weight vectors, and the height of the loss, the color is the value of the loss of that combination. And so these visualizations are in collaboration with Javier IDM, losslandscape.com, very cool website. Here we have several other visualizations of mode connectivity. We can see even in the two-dimensional slices that the structure of the loss surface is extremely complex, multimodal. Why would we choose just one of these points? So the next question to ask is whether we can actually recycle geometric information in the SGD trajectory for scalable posterior approximations centered on flat regions of the loss. So this mode connecting result is very significant in the sense that it empirically verifies this diagram that was used to motivate sort of flat optima. It shows that, in fact, there are these extraordinarily flat regions of the loss surface. And in fact, as we'll see, they contain a variety of different solutions. We really want to do this integral. And we want to see now how we can practically kind of learn something about the shape of the loss surface just through something that resembles kind of basic SGD training. And so we found that if we used a learning rate schedule that decayed to a relatively high constant learning rate and took an equal average of the weights traversed by SGD with that high constant learning rate, we were spinning around a region of the loss surface that contained a bunch of different models which all had very low training loss. And so normally it'd be very hard to penetrate inside that region. But when we're spinning around, we can take an equal average of the iterates. It's very important this is an equal average and a constant learning rate schedule. We can move inside to a fairly centered region. So this is, and that those solutions in this procedure called stochastic weight averaging often lead to much better generalization without a lot of additional computational overhead. And so this is very, importantly different than, say, Polyak Ruppert averaging, where often we're using exponential moving averages with decaying rates, and the idea is to get better convergence, say, in convex optimization. Now, in addition to taking the mean of these SGD iterates, we can also come up with a low rank plus diagonal approximation to the second moment, the covariance matrix. And then we can use that to come up with a Gaussian approximate posterior for our parameters. And then we can use that and sample from it to get our simple Monte Carlo estimate of our predictive distribution. And the whole method here, called SWAG, S-W-A Gaussian, because it's a Gaussian approximate posterior using ideas kind of motivated by SWA, can be written here just on, just one on this one slide. And that's why we call it a simple baseline for Bayesian uncertainty in deep learning. Now, there's theory suggesting that if we run SGD with modified learning rate schedules asymptotically, we're sampling from a Gaussian distribution, which is a reasonable description of the posterior. However, this theory has assumptions which are violated in deep learning. So as a sanity check, we also visualized the loss surface in the subspaces spanned by the principal components of the SGD iterates with these modified learning rate schedules, and showed that the SWAG procedure came up with a pretty good posterior approximation of the loss surface in these subspaces. Here we're considering the calibration of various models. So on the vertical axis of each of these plots, we have confidence minus accuracy. Confidence corresponds to the highest softmax output in our ConvNet, and accuracy is the accuracy of using the associated class label. And so here, a horizontal curve at 0 corresponds to a perfectly calibrated model. A curve above that horizontal curve corresponds to overconfidence, and below that curve corresponds to underconfidence. And the horizontal axis here, we just have bins for different confidence levels. So green is SGD training. We see that it's almost always overconfident, And in a way that isn't surprising because those models are ignoring epistemic uncertainties. So they're, in classical training, we're betting everything on a single model, whether or not it's regularized. And this means that we're ignoring all the other possible functions that are consistent with our observations. So of course, in a sense, we're overconfident. When we try to account for epistemic uncertainty through model averaging that we get through SWAG, for example, then we see in many cases we end up with quite good calibration. We're also considering a number of other approaches. So SWAG here is in blue, we have a dropout-like approach in gold, we have K-FAC Laplace in pink, temperature scaling procedure in brown. We can also notably see in the bottom row here, we have ImageNet results with huge neural nets, like a DenseNet 161 or a ResNet 152. And so this is a very scalable procedure. It can be applied virtually wherever you would just do standard classical SGD training. And in the top right, we have a transfer learning problem, which is important because a lot of non-Bayesian alternatives like temperature scaling, where we just scale all our logits by a particular parameter, the logits just before we pass through the softmax, a special case of Platt scaling, require a validation set that's really representative of the target distribution, and that's hard if we have covariate shift. And so capturing epistemic uncertainty is going to be especially robust in these kinds of settings compared to the alternatives, but still we see all the different approaches here are overconfident to some extent. We can very naturally visualize epistemic uncertainty in regression problems. So here we see that with the SWAG method, as we move away from the data point, we're getting a wider predictive distribution. And this is because there are many different types of curves that are consistent with our observations away from the data, but not towards the data. We become constrained. And so that's really what epistemic uncertainty is trying to capture, compared to, say, aleatoric uncertainty, which would correspond in this case to noise in the measurements themselves. On the other hand, we see with the full space VI, using standard variational approach for approximate marginalization of neural net parameters, we get a reasonably good mean fit point predictions, but the uncertainty is pretty homogeneous and it doesn't grow that much as we move away from the data. So it's not doing a great job of epistemic uncertainty representation. So in short, this SWA Gaussian SWAG procedure provides a simple and scalable method for Bayesian deep learning. Idea is just fit the SG iterates to a low rank plus diagonal Gaussian distribution, and we can capture geometric properties of the posterior in a subspace of SGD, and we can improve predictions and uncertainty at the ImageNet scale. Now, in order to motivate this SWAG procedure, we created a visualization of the subspace spanned by the principal components of the SG iterates. And this led to the question of whether it might make sense just to try to do Bayesian marginalization in the very low dimensional subspace directly. And so here we're saying, let's construct a subspace of a network that has a very high dimensional parameter space, perform inference in that subspace, and then sample from the approximate posterior just using Bayesian, and then use those samples for Bayesian model averaging. And what we found is that we could approximate the posterior of a wide ResNet with 36 million parameters in a 5D subspace and achieve state-of-the-art results. So the contention here is that even though the parameter space is very high dimensional, a lot of the functional variability could be captured in a very low dimensional subspace. And once we reduce that integral that we're trying to compute to a very low dimensional integral, then it's going to be a lot easier to estimate. So a lot of the challenges with Bayesian neural nets are around the fact that we have to compute this very high dimensional integral typically. So in particular, in this approach, what we did was we collected all the weights of the neural net and said they were equal to an offset, like the SWA solution, plus a linear projection P of a very low dimensional vector Z. And then we did inference in Z space, so we could even use slice sampling if we're in a low enough dimensional space, which is a really great MCMC method, but it has a cursive dimensionality. Then we can sort of use this equation to go back into W space and do the Bayesian model average. So let's first consider the mode connecting subspace. So in the right panel here, we're traversing through parameter space in this mode connecting subspace. And in the left panel, we're looking at the corresponding functions in purple. And we can see first that there's a lot of functional variability in this very flat region of the posterior. And if I were to ask you which curve you preferred, this purple curve or that purple curve, you probably have a hard time saying. And this is why it's quite arbitrary just to bet everything on one solution. We want to consider all of these solutions in forming our predictive distribution. When we do that, we see we get good epistemic uncertainty representation. We can see that the spread of the predictive distribution here, showing the 95% credible set, increases as we move away from the data, decreases as we move towards the data. Here we consider two other subspaces, the random subspace and the PCA subspace. Random subspace is what we get when we just use samples from a Gaussian distribution for our projection matrix, independence, standard Gaussian. And we can see that the curve that here actually fits the data pretty well in terms of point predictions, but the uncertainty is very homogeneous. So we're not doing a good job of epistemic uncertainty representation. The bottom row here, we see the subspaces in parameter space. So each point is sort of a different composition of parameters, and the colors correspond to the values of the loss at those points. In the middle column here, we have the PCA subspace, which is what we get when that projection matrix is found by looking at the principal components of the SG iterates. In particular, as we're traversing the loss surface with this high constant learning rate schedule, we can store a matrix which has its columns, the weights that we're passing through, minus the average of those weights, and then we can do a partial SVD, and that gives us our projection matrix. It's super efficient. It's just a single computation, and once we've got that subspace, we perform inference, and we can see that we get a pretty good predictive distribution here, which is doing an intuitively good job of representing epistemic uncertainty. Now, in part one, I emphasized that because there's all this functional variability inside the loss surface of a neural net, we're really going to benefit not just in terms of uncertainty representation, which can be measured by, say, negative log likelihood, but also in terms of just the accuracy of our point predictions. And we can really realize that here with that subspace approach. So here we have a ResNet on CFAR 100. It's getting 78.5% accuracy with classical SGD training. It's getting 80.17% with the random projection. And we're getting 80.5% then with the PCA subspace and 81.28% with the curve subspace. So these are really non-trivial gains in accuracy. And the PCA subspace, for example, is not really much more expensive than just classical training. And so we can really empirically realize the benefits of Bayesian marginalization in terms of not just uncertainty representation measured by NLL, which we see is also increasing or decreasing, but also accuracy. So historically, the Laplace approximation has been very important in performing inference with Bayesian neural nets. David Mackay, who did a lot of the first work in this space, was considering Laplace approximations, and recently they've come back with Kronecker factorizations. So the basic idea is we approximate the posterior with a Gaussian, has its parameters theta, its mean mu, and its covariance matrix A inverse. And these parameters are determined by a second order Taylor approximation around the log unnormalized true posterior PW given D. When we do that Taylor expansion, we see that we set the mean equal to the map setting of the parameter is what we get when we maximize the posterior with respect to W. And we set A equal to the negative Hessian of the log posterior evaluated at W map. So for a high dimensional parameter space, this A matrix is way too large to store. So, if it's a W is 10 million dimensional, typically A is taken to be diagonal, like in David Mackay's work, or recently K has been expressed as a Kronecker product of much smaller matrices, which is more expressive than the diagonal approximation and leads to better results, but it's still scalable. And once we have our Gaussian approximate posterior, we can sample from it using a simple Monte Carlo estimate of our unconditional predictive distribution. So overall, the Laplace approach is compelling because it's simple and can be relatively efficient. Perhaps as a drawback, it's constrained to unimodal approximations. It's a Gaussian approximate posterior, and it's fairly local in its description of the loss, even for a Gaussian. So the curvature is entirely defined by the Hessian evaluated at that map setting of parameters. And so this means if, for example, there's a little kink in the loss surface, then it'll be very concentrated around a very small region. It'll be a very, very compact representation of the posterior. SWAG, by contrast, even though it provides a Gaussian approximation, it's more global because we have SGD with this fairly high constant learning rate bouncing around within some basin of attraction. And so if there are little kinks, we'll still get a fairly kind of global Gaussian approximation that won't be trapped in those regions, at least for that basin. MC dropout is another very popular approach for Bayesian neural nets, and really catalyzed a lot of renewed interest in Bayesian deep learning in 2016. And so the idea is to run dropout during both train and test. You randomly drop out each hidden unit with probability R at each input. And this creates a mask. In regression, each network can be trained to output both a mean, mu, and a variance sigma square by maximizing a Gaussian likelihood. We then create an equally weighted ensemble of the corresponding subnetworks with a different dropout mass at test time. So this is a very compelling approach. It's very easy to apply, it's very scalable, and it's had great empirical results in representing epistemic uncertainty and a number of problems. We know in this case, the ensemble doesn't collapse as we get more data, unlike a standard Bayesian model average. So in part one, we considered how Bayesian model averaging isn't sort of model combination in the sense that it's just representing a statistical inability to distinguish between hypotheses given limited information. Whereas here, we're still going to be sampling from this Bernoulli distribution to get the dropout mass, and so this isn't something that collapses as we get more data, and figure out how to maybe modify it for that would be an interesting direction for future work. So another historically important approach for Bayesian deep learning is called Bayes by backprop. This is where we introduce typically Gaussian approximate posterior for our parameters. And then we learn those parameters using a variational method, which minimizes the KL divergence between our approximate posterior and the true posterior. Even though we can't integrate with respect to the true posterior, we can usually write down the unnormalized true posterior exactly. We just multiply our likelihood and our prior, and we can manipulate the KL divergence to get an evidence lower bound, which can be optimized with SGD and backpropagation. So even though in principle we can choose sort of different distributions for Q, it is often a lot easier to use Gaussian. Stochastic MCMC is a very up-and-coming direction for Bayesian deep learning. So Radford-Neal's MCMC methods in the mid-90s were achieving state-of-the-art results for all sorts of interesting problems, but these standard Hamiltonian Monte Carlo methods wouldn't really scale to big architectures. Stochastic gradient Langevin dynamics and stochastic gradient HMC, for example, on the other hand, are very broadly applicable. They algorithmically resemble SGD, noisy SGD, pretty closely. UW here is a log posterior, and so we can really apply these wherever we apply SGD and often achieve better results through the Bayesian model average. Now, when we're doing optimization, even though we sort of explore the loss surface to try to find a good solution, in the end, all we care about, in principle, is finding a solution with low loss. Whereas when we're sampling and when we're doing Bayesian model averaging, we really care about exploring this surface. And so in this case, the learning rate schedule is particularly crucial for good performance. And it's recently been found that a cyclical learning rate schedule can really greatly enhance the ability for the stochastic MCMC procedure to explore complex multimodal loss surfaces and achieve much better practical performance. So here we increase the learning rate and we're sort of exploring, and then we decrease and we sort of explore within a mode and use those samples. Deep ensembles has recently gained a lot of popularity and has achieved a lot of success. The idea is to specify a neural net architecture, retrain the neural net a bunch of times to get a bunch of different SGD solutions, typically starting from different initializations. So we get a bunch of different weights. And then, again, in regression, each model can be specified to output a mean, mu, and a variance sigma squared trained through, say, a Gaussian likelihood. And once we have all these different architectures corresponding to the different weights that we found through SGD retraining, we take an equally weighted ensemble. So you might be wondering, why is deep ensembles in a section about practical methods for Bayesian neural nets? Are deep ensembles Bayesian? In fact, aren't they often explicitly treated as a competing approach to Bayesian methods? In the next part, part 4, we'll argue that deep ensembles in fact provide a better approximation to Bayesian model averaging than many of the methods that we've described so far that provide single basin marginalization. We'll also introduce an approach multi-swag which generalizes deep ensembles for even more accurate Bayesian model averaging. We'll note briefly now, though, that, for example, the average here, unlike with MC dropout, actually does collapse in the same way as a Bayesian model average. And so, for example, we're not enriching the hypothesis space. We're just using the same architecture retrained a bunch of times with different maximum likelihood or map solutions. So as the likelihood collapses, so will the Bayesian model average, and so will this ensemble. Also, by looking at different basins of attraction, we're capturing functional variability, which intuitively is going to be very important for estimating this Bayesian predictive distribution when we're trying to do marginalization, when we're trying to estimate that integral. And given a finite amount of computation, being able to spread where we're querying the loss surfaces across different basins of attraction is going to be very important for coming up with a good approximation to that integral. So in a sense, it's doing very well at approximating the Bayesian predictive distribution, given a finite number of resources. Next, we'll have part 4 on Bayesian model construction and generalization. Hi, I'm Andrew Wilson at New York University, and welcome back to the ICML 2020 tutorial on Bayesian deep learning. This is part 4 on Bayesian model construction and generalization. In this part, we'll consider deep ensembles and their connection with Bayesian marginalization. We'll use this connection to describe multi-swag, a procedure which marginalizes within multiple basins of attraction. We'll also consider tempering, prior specification, rethinking generalization, double descent, and width-depth trade-offs. Here we'll return to a function space perspective that we considered in depth in part 2. We have a straight line function with a distribution over its parameters, W0 and W1. We can visualize this induced distribution over functions by sampling from this distribution over parameters and looking at the different straight lines we get with different slopes and intercepts. The gray shade here corresponds to a 95% credible set, and the solid blue line corresponds to the expectation of this distribution over functions. In this diagram here, we have a conceptualization of all possible data sets on the horizontal axis, and the marginal likelihood, or evidence, on the vertical axis, expressed in equation 74. The marginal likelihood is the probability that we would generate a data set if we were to randomly sample from the parameters, the distribution over the parameters of our model. We can see here in equation 74 that the marginal likelihood is what we get when we integrate away these parameters. In the example from the last slide, we're just generating straight lines with different slopes and intercepts. So we're not able to generate many data sets at all, but because the marginal likelihood is a proper normalizable probability density, it'll have to assign a lot of mass to those data sets. Alternatively, we can consider a model like maybe a huge multilayer perceptron with a broad distribution over its parameters, which can generate lots of different data sets, but each with not very much probability. We could alternatively consider a model like a convolutional neural net, which is very flexible, so it can generate all sorts of different data sets, but it has very particular inductive biases like translation equivariance, this idea that if we translate an image, its class label remains unchanged. And so it will give a lot of mass to structured image data sets. In order for a model to generalize, it needs to both have large support, it needs to be very flexible, and it should have good inductive biases, a good distribution of that support. So models like convolutional nets can generalize very effectively on image recognition problems because it supports all sorts of different data sets in this application domain, but it has a good distribution of support through biases like translation equivariance. We should be very careful not to conflate flexibility and complexity. As we were describing in part 2 of the talk, we can have models like Gaussian processes, which are extraordinarily flexible, even universal approximators, but in a sense, have very simple inductive biases and can generalize very well on problems with even a small number of data points. In this figure here, in addition to the panel that we considered on the last slide, we look at what happens as these three models are exposed to a given data set. We can see that the model with large support but good inductive biases both contains the ground truth description and is able to contract efficiently around it. The model with truncated support contracts quickly. It's quickly constrained by the available data, but it contracts around an erroneous solution. The model with large support but poor inductive biases that spreads its support too thinly across too many data sets contains the truth, but it doesn't contract very efficiently. At the end of the last part 3, we were considering deep ensembles, and we started to hint at their potential connection with Bayesian marginalization. Recall that the predictive distribution that we want to compute is this integral of our conditional predictive distribution given parameters, weighted by the posterior probabilities of parameters given data. And so we want to, in words, consider every possible setting of the parameters and weight them by their posterior probabilities. Now, this Bayesian approach and the classical approach will be similar when the posterior is very concentrated around a small number of parameters, or when the conditional predictive distribution y given w is not varying a lot, where the posterior distribution w given d has most of its mass. Now, in this top panel here, we have a conceptualization of the posterior distribution for a neural net. Multimodal, lots of global optima. And in the second row, we have a conditional distribution. Now, with a deep neural net, there isn't a lot of functional variability within a single basin of attraction compared to between different basins of attraction. So we can see that conceptualized in this second row, where we see that P of y given w doesn't change very much within a basin, but it changes a lot between the basins. In the bottom row here, we're thinking about estimating this integral as an active learning problem. We've observed a single solution, say an SGD solution here in one of the basins, and we're seeing where we need to move in weight space to decrease the distance between our approximate predictive distribution and the exact predictive distribution, the exact answer to this integral. And we can see that we would benefit a lot more by moving to a new basin than continuing to query points within the same basin. And so, indeed, a lot of approaches to Bayesian marginalization focus their efforts just on a single basin. They do Gaussian approximate posteriors. But in deep learning, if we view this integration problem as really an active learning problem rather than through the lens of simple Monte Carlo, then it's very advantageous, given finite computational resources, to do something like deep ensembles and just select points from different basins, and we'll get a better approximation to this integral, and in fact a more Bayesian approach than the Bayesian approaches which are marginalizing within a single basin. So we're in practice, in real world, we're always handed computational constraints, and we try to do our best given those constraints. And deep ensembles is actually a very good heuristic for achieving a good approximation to this integral given those constraints. Here, we empirically test how close the deep ensembles predictive distribution is to a near exact predictive distribution, which we can see in panel A. In panel B, we have the deep ensembles. We can see visually it's fairly similar to the exact distribution. In panel C, we have a variational procedure doing single basin marginalization with a Gaussian approximate posterior. We can see that it doesn't capture epistemic uncertainty so well. It doesn't have a lot of uncertainty between different clusters of data points. The uncertainty doesn't grow very consistently away from the data. In the bottom right panel, we look at what happens as we, in terms of the distance between the approximate predictive distribution given by both deep ensembles and stochastic variational inference as we increase the number of samples we have access to. And we can see that that distance decreases very quickly for deep ensembles, but hardly at all as we increase the number of samples that we have with the variational procedure. So continuing to see samples within a single basin with this variational approach is not really improving our estimate of the Bayesian model average corresponding to this integral that we want to compute. But training more models in the deep ensembles is pretty dramatically decreasing the distance between our approximation and the exact answer. So in addition to just selecting different points in different basins, we can also try to marginalize within basins of attraction. And we do that in a procedure called multi-swag, where we train multiple independent swag methods discussed in part 3 to create a mixture of Gaussian's approximation to the posterior. So we're marginalizing within multiple basins. When we do that and apply multi-swag to several of the applications in reference 1, evaluating predictive uncertainty under dataset shift, which showed that deep ensembles often outperform single basin marginalization procedures, we see 2 key trends. One is that multi-swag tends to significantly outperform deep ensembles in cases where we're not training very many independent models or when there's a lot of data corruption. In purple here, we have an additional model, multi-SWA, which takes the means of the different Gaussian components in multi-swag, and that those will be in flatter regions of those different basins of attraction than say SGD solutions. And so we see a nice compromise here. Recently, a phenomenon called double descent has been of great interest. Belkin et al. A couple of years ago showed that we could find these so-called double descent curves on a wide range of problems where we have our loss on the vertical axis, and we can see as we increase model flexibility, initially loss appears to be decreasing, and then it increases, corresponding to overfitting, and then it turns out it decreases again. And so this first regime is called the classical regime, which is in line with classical intuitions about generalization, and the next regime is referred to as the modern interpolating regime. So the training loss here just keeps going down. The test loss has this really non-monotonic behavior. And the question is, well, why don't we just keep overfitting? Why does suddenly generalization start getting better, especially once we move past where the training loss is 0? So I'd like to ask you, and feel free to pause the video for a moment, whether you think a Bayesian model should experience double descent, given what we've discussed so far. And considering this problem, especially think back to that first example at the beginning of the talk, where we're considering airline passenger numbers and which model we would want to fit that data with using a Bayesian approach. So in that airline passenger number examples, I was saying that if we have a reasonable prior and we're doing exhaustive marginalization, then we would expect a Bayesian method to improve monotonically with increases in flexibility. We should embrace flexibility, have large support. And indeed, that is actually what we see if we apply this multi-swag procedure. We see that performance is essentially monotonic, whereas SGD, in this example where we have CFAR 100, 20% label corruption, has a prominent double descent behavior. Swag, where we're doing single basin marginalization, has a less prominent double descent, but it's still clearly there. Another really important feature to note in this plot is the fact that multi-swag is actually just a lot more accurate than classical training. So if we have a ResNet with layers of width 20 here, we see just below 30% test error on CFAR 100, whereas if we're using SGD, we see about 45% test error. So it's a really massive discrepancy, and an empirical realization of this idea that if we're doing multimodal marginalization with a neural net which can capture all sorts of complementary explanations to the data, then we're really going to benefit a lot empirically, not just in terms of uncertainty representation, but also in terms of accuracy. Now we'll consider the prior in function space that's induced by having a Gaussian prior in weight space, where we're just varying the signal variance of the prior for each of the parameters alpha squared. And so there are 2 key results that suggest that this actually induces a pretty reasonable prior in function space. First is the deep image prior, which showed that randomly initialized convnets without training provide excellent performance for image denoising, super resolution, and inpainting. In other words, a sample function from this induced distribution over functions captures low-level image statistics before any training. Another result from the paper by Zhang et al. On rethinking generalization shows that if we pre-process CFAR 10 with a randomly initialized untrained CNN, we get dramatically improved test performance when we're using a Gaussian kernel directly on pixels. So it goes from 54% accuracy to 71% accuracy. And then we just get another 2% from L2 regularization, which would be like tuning this alpha perimeter. And so this is really saying that this induced distribution over functions is fairly reasonable. And in a way, it's not surprising because the properties of the induced distribution over functions comes largely from the functional form of the model. That's really a big part of the prior translation equivariance in sort of a similarity metric that we get for different images, et cetera. You know, this is going to come from mostly the functional form of the model. Now, in Bayesian deep learning, it's typical to consider what's called a tempered posterior, where we've raised the likelihood to a power 1 over t, where t is a temperature parameter. T less than 1 corresponds to a cold posterior, where the posterior is more concentrated around solutions with high likelihood. T equals 1 corresponds to the standard Bayesian posterior. T is greater than 1 corresponds to warm posteriors, where the prior effect is stronger and posterior collapse is slower. In a paper at this ICML by Wenzel et al., there's a result that's highlighted that with a standard Gaussian prior over parameters, cold posteriors often provide improved performance, but if we use just a temperature equals 1, we can get even worse performance than classical training. In this paper, they suggest the result is due to prior misspecification and show here that sample functions from this induced distribution over functions with the standard normal prior seem to assign one label to most classes on CFAR10, and we know the classes are balanced. So here we just sample from the standard normal, get our function with our neural nets, and we see that it's giving most of the data points class 6 here, and then another sample function is giving most of the data points class 9. We examine this behavior as we vary the scale of the prior variance on the parameters. So for alpha equals root 10, we reproduce this result, and we see that one sample function is assigning most of the data one class, another sample function most of the data the other class. However, if we reduce alpha, we see that the samples are very quickly assigning about the same amount of data to each of the classes. And in fact, of course, in practice, we would specify alpha through cross-validation or through, for example, just what we normally use for L2 regularization, which is roughly near 0.1 in this case. We also see that even for the misspecified alpha, the unconditional predictive distribution is actually quite reasonable. It's basically uniform over the different classes, so it doesn't affect the predictions. We can also examine the effect of data on the posterior here. So here we start with the prior, the misspecified prior, that where sample functions are assigning most of the data one class. We then observe just 10 data points with this huge ResNet, and we see that already the samples are giving almost uniform predictions across the different points, 100 data points, even closer to uniform. And so this is a prior bias that is very quickly modulated by data. We can imagine with a Gaussian process, for instance, if we multiplied our kernel by some factor, the amplitude would be off. But if we observe just a few data points, the posterior would quickly collapse in that region. So this is the kind of prior bias which isn't really going to affect generalization that much in practice. What's much more important, for example, is the induced covariance function that we get in this distribution over functions. And we saw this a bit in part 2, where things like covariance function really affected generalization. So here we have the induced correlation function for MNIST digits, different classes. We can see that the correlations generally decrease as we increase alpha. We also see that pretty consistently the same classes are most correlated, and classes that are visually similar are more correlated than other classes. This is a good sign. This is also suggestive, in addition to the deep image prior and the random network features, that we're inducing a prior that is actually pretty reasonable. And which covariance function, for example, you use in a Gaussian process is going to affect generalization much more than whether you have a signal variance parameter that's a bit misspecified. So some thoughts on tempering. I think it would be very surprising if t equals 1 just happened to be the best setting of this hyperparameter. In fact, I think we should always be doing tempering. It's basically just an acknowledgement that our model is misspecified. That's not to say that we should, just say, well, who cares about the model specification? We'll correct it with tempering. We should do our very best to specify our prior as honestly as we can. But it's still going to be misspecified, and we should be honest about that too, and try to correct it by learning the temperature. And in fact, this isn't really too different than learning other properties of the likelihood, like noise. Now, while the prior P of f of x is certainly misspecified in most cases in Bayesian deep learning, the result of assigning one class to most data is really a soft prior bias, which one, doesn't hurt the predictive distribution, two, is easily corrected by appropriately setting the prior parameter variance alpha squared, and three, is quickly modulated by data. What's much more important is this induced covariance function over images. In addition to not tuning alpha in this whole posteriors paper, the results could have been exacerbated due to lack of multimodal marginalization, which we've shown is extremely important for generalization. It's also interesting to note that there are cases when a cold posterior, a t less than 1, will be helpful in coming up with estimates, even if we believe the prior and the likelihood, if we have access to a finite number of samples. So we can imagine, for instance, estimating the mean of a standard normal distribution in high dimensions. In this case, the samples will be very concentrated around a norm of root d. And so if we decrease the temperature, we'll come up with a better estimate for the mean. And so I encourage you to try this. Just sample from a high d distribution, look at a histogram of the norms. So there was a paper a few years ago called Understanding Deep Learning Requires Rethinking Generalization. They showed that conv nets could fit CFAR with random labels. And this was presented as if it were in the face of everything we know about generalization, because it showed that the conv nets could fit in noise. They could greatly overfit, yet they were generalizing on all sorts of different problems. We can understand this result from the probabilistic function space perspective. So in the top row here, we have samples from a Gaussian process in panel A. In panel B, we see some structured data and a Gaussian process predictive distribution, which looks reasonable. In panel C, we see a lot of corrupted data in red, and we see an updated GP predictive distribution, which achieves 0 training error. Now, this red curve, unlike the green curve in panel B, looks nothing like the sample prior functions. However, the GP with the RBF kernel is very flexible. It contains somewhere in its support this red curve, even though we might have to sit there sampling for a very, very long time to see anything like it. However, if there's a strong enough likelihood signal, we're saying there's no noise, then it's going to run through that data perfectly and produce this predictive distribution. And so it doesn't want to fit that data, but it can. And we can quantify how much a model wants to fit data with something called the marginal likelihood. And so we can actually fit a Gaussian process on CFAR10 with altered labels and show that we get 0% training error. So that means that this result in the Rethinking Generalization paper wasn't unique to deep neural nets. You can reproduce it with Gaussian processes. And we can also compute the approximate marginal likelihood and show that it gets very, very low as we increase the number of altered labels. So that noisy CFAR set is somewhere in the tails of that distribution where we're considering all possible data sets and the marginal likelihood on the vertical axis when we're considering this GP model with an RBF kernel. We can also compute exactly the same thing using a Bayesian neural net, find the approximate marginal likelihood using Laplace, and we see that it decreases in the same way as we increase the number of altered labels. So this Bayesian neural net is able to fit that kind of data set, but it really doesn't want to. And we can quantify that with the marginal likelihood. And this is sort of in accordance with what we would want when we're thinking about model construction. We want large support, but we want to distribute that support carefully. And that means not giving a lot of mass to things like noisy CFAR. But if we see noisy CFAR, there's a strong likelihood signal and we can fit it. Okay, so of course, having said all that, the priors in function space aren't going to be perfect by just having sort of generic Gaussian distributions over parameters combined with functional forms of neural nets. And we can certainly do better. And I certainly embrace the function space perspective in constructing compelling priors for these neural nets. At the same time, we should be careful not to contrive priors over parameters W to induce distributions over functions that resemble familiar models, such as Gaussian processes with RBF kernels. We could be throwing the baby out with the bathwater in doing that. Indeed, neural nets are useful as their own model class precisely because they have different inductive biases from other models. We already have Gaussian processes with RBF kernels. And we can try to gain insights in thinking in function space, but this is, in a sense, what we're already doing when we're doing architecture design. That's thinking in function space, trying to encode properties such as translation equivariance, rotation equivariance, color and scale invariance, and other interesting properties that would induce a compelling similarity metric across our data instances. And so these properties really imbue the associated distribution over functions with desirable properties for generalization. And really all of the heavy lifting for the prior over functions that we get is from the architecture. And you know, even if we're thinking more broadly, the functional formal model is like a strong prior. It's a very strong assumption. We can't escape assumptions, and we shouldn't try to. We should embrace assumptions. They're, you know, we need to make assumptions to have good generalization. Pak-Bayes has been a very exciting approach for deriving explicit generalization error bounds in stochastic networks with posteriors Q, prior P, training points N. The Pak-Bayes generalization error bounds are based on this term in equation 79, and we've recently you know, people have derived non-vacuous bounds exploiting flatness in Q with at least 80% generalization accuracy predicted on binary MNIST. So this is, you know, very exciting. It's a promising framework, but it tends not to be prescriptive about model construction or informative for understanding why a model generalizes. So in a sense, it's very complementary to what we've been describing so far in this tutorial. And in fact, if we were to try to treat it as a prescription, what we would get is sort of almost contrary to a lot of what we've discussed. The bounds are improved by compact priors, for example. And we've been saying, well, we want priors with support for all sorts of different data sets. And a low dimensional parameter space, in a sense that the KL divergence is going to be often sort of hard to assign a lot of overlap between two high dimensional distributions. And so we can very often achieve better bounds by doing model compression, etc. But here we've really been trying to embrace having as many parameters as possible for good generalization. Also, generalization, as we've shown, can be significantly improved by a multimodal posterior, especially in Bayesian deep learning. This is, you know, really one of the key practical takeaways. And in order to realize a good approximation to the unconditional predictive distribution, we really need to do multimodal marginalization. But the Pak-Bayes generalization bounds aren't typically too influenced by multimodal posteriors. You end up with a log factor. It doesn't really change things that much. So the Pak-Bayes bounds are quite complementary, and they're very exciting in the sense that they help us make sort of quantitative, sort of explicit statements about generalization error bounds. But they don't tend to be too prescriptive. And this could be partly also because although we in some cases get non-vacuous bounds, they're also typically fairly loose. So what improves the bounds won't necessarily improve generalization. We can relate posterior contraction to a quantity called effective dimension and actually gain insights into behavior such as double descent. So effective dimension is the Hessian here is the sum of lambda I over lambda I plus alpha, where alpha is a regularization parameter and lambda I are the eigenvalues of the Hessian. When we compute this quantity of networks, ResNets of varying width here, we can see that it tracks test loss very closely, as well as, you know, test error. And in fact, the effective dimension is going down as we increase the size of the models. And this suggests that actually we're getting simpler models, even though they have more parameters. So we should be very careful not to treat parameter counting as a proxy for model complexity. And we can relate effective dimension to model compression. In a sense, this sort of counts the number of kind of sharp directions in this space given by the eigenvectors of the Hessian. And we can see that in this regime where we have basically zero training loss, all the different models are providing lossless compressions of the data. And so the best compression will capture the most regularity. It will have this sort of Occam's razor property and tend to provide the best generalization. Now, the reason SGD finds these kinds of solutions when we make the model size bigger is largely because you know, flat region of the loss will occupy a much greater volume in high dimensions. And so SGD will be able to find them more easily. We also look at width-depth trade-offs, so looking at convnets of different widths and depths, and we can see above the green partition where we have zero training loss. Effective dimension is a very good proxy for generalization performance. The yellow curves here show level curves of constant numbers of parameters. You know, it's interesting here especially to consider different depths. Typically, in recent years, we've been looking at infinite widths of neural nets for neural tangent kernels and things like this. But in a sense, depth is what gives deep learning a lot of useful hierarchical inductive biases that provides good generalization and representation learning. And so we can see that this quantity associated with posterior contraction in Bayesian deep learning is a reasonably good proxy for generalization. We can also look at the properties in function space as we move in directions given by eigenvectors of the Hessian with the smallest eigenvalues, and show that the decision boundaries are essentially unchanged, that we get a lot of functional homogeneity. And this provides a mechanism for why things like subspace inference, discussed in part 3 of the talk, work so well, why we can have a model with tens of millions of parameters and then basically just do marginalization in a 5-dimensional subspace and see a big difference for that. And so we can really understand things like model compression by looking at these quantities. In conclusion, what we've been really reiterating through this tutorial is that the key defining feature of Bayesian methods is marginalization, aka Bayesian model averaging, and that's going to be especially relevant in deep learning because neural nets are very underspecified by the data, contain all sorts of complementary and exciting solutions to a given problem, and it really makes a lot of sense just to use the sum and product rules of probability to marginalize those solutions. And really, in trying to do this marginalization as best as we can, we shouldn't think of the integration purely through the lens of simple Monte Carlo integration. We should probably think of it more as an active learning problem, and by doing that, we can gain insights into methods like deep ensembles and also propose other kind of Bayesian methods that provide even better marginalization, like multi-swag. I'm very excited to say in the last year or so that a lot of Bayesian methods are now providing better results than classical training, both in terms of accuracy and uncertainty representation, without a lot of additional overhead. Really, this emphasizes that there's a big difference between marginalization and just regularization, as we saw in that coin toss example. We should be careful not to conflate flexibility and complexity. Gaussian processes, for instance, can be extremely flexible of an infinite number of parameters, simple inductive biases, good generalization on a small number of points, and also careful not to parameter count as a proxy for complexity. Sometimes the models with many more parameters, in a sense, are helping us find simpler solutions. And we can really resolve a lot of mysterious results in deep learning by thinking about model construction and generalization from a probabilistic perspective. So that's everything, and I really like to thank you for attending this tutorial.